Okay, so I'm sorry that I forgot to record on both sections. Here is what we have talked about. So in the previous pages, we have talked about how to construct confidence intervals using the t-score or z-score. That's something we have talked about before the spring break. So I want to summarize a little bit of what we have talked about here. So first, in order for us to use all those t-scores or z-scores formula, you have to satisfy some conditions. First is it has to be a random sample. Second, it has some assumption about the population distribution. I'm going to summarize it in a small table here. Let me make this line a little bit straighter. Okay, so when your population distribution is normal, we have talked about it in the central limit theorem, that no matter what your sample size is, your sampling distribution of the sample means will be normal. So when your sample size n is small, when sigma is known, we have talked about that, we are going to use the formula for the z-score, I'm sorry. When your sigma is unknown, we are going to use the formula for the t-score. When your sample size n is big, things are the same. When your sigma is known, we could use the z-score. When sigma is unknown, we could use the t-score. One thing here is, remember we said that as sample size n gets larger and larger, the t distribution will be closer and closer to a standard normal distribution. So when sample size n is big, this actually could be approximately a normal distribution. So we could use z formula as well as approximation, but the precise distribution is to use the t-score. When you don't know your population distribution, things are a little bit tricky. So when your sample size n is small, then that's not something that we have talked about. When you don't know your population distribution, it may be pretty skewed, and your sample size n is pretty small, then that's not something that we could answer in this class. So you will need some more advanced stats here. But when your population distribution is even though unknown, but your sample size n is big enough, then we could still use this. And again, as I mentioned, your t distribution could be approximate by the standard, by this z-score here. So one thing that I would like to mention here is this interval estimation that we have talked about is kind of like a robust estimation. What does it mean by robust estimation? That means it's kind of like okay estimation even though your assumption is violated. So this interval is typically robust to assumption of normality. That is, Even though your population distribution is not exact normal distribution, but as long as it's not highly skewed and your sample size is large enough, your probably is going to be okay. So the interval is typically robust to assumption of a normality, especially when your sample size is large. So this is what I try to summarize here. So the conditions, first, it has to be a random sample. Second, the population distribution needs to normal. Or if your population distribution is not normal, then the sample size n needs to be big. Now let's take a look at this example here. I give you some time to work on this example during the class. Now I'm going to go ahead to talk about it directly instead of leaving some time here. So in this example, we claim that the mean age at which children start walking is 12.5. Now this person, Carol, collect a sample. Sample size n equals 18, and the sample mean is 12.9, and the sample standard deviation is 0.8. So in this question, the sample size n is not too big, but we kind of like could assume the population distribution is normal because this is the mean age at which children start to walk, right? So it's reasonable to believe that the population distribution is normal, at least symmetric. So we could go ahead to use our formula of the t distribution here. Square root of n, because we don't know the population standard deviation, so we are going to use this z, this t formula. So you plug in the numbers, we got 12.9 plus or minus 0.8 divided by square root of 18. The only thing left unknown is this t-score here. Now, usually what we are going to do is we are going to refer to the table or the StatCrunch to find this number, right? But here in this case, it's actually provided to you. So we are trying to find the 99% confidence interval, right? So the area in the middle is 99. So the confidence level is 99. So what do you think is our alpha? Our alpha is going to be 1%. So our alpha over 2 is going to be 0.005. So the area here is going to be 0.005, and so does the area to the left of it as well. So what are we trying to find out is this value here, right? This value under the t distribution with degrees of freedom equals n minus 1, which is 17. What is this value that will make the area under the curve to the right of it equals to 0.005? In other words, what is the value that will make the probability that the t distribution greater than this value is 0.005, given that this t distribution has a degrees of freedom equals 17. So it is here that we are looking at. So this is a t distribution with degrees of freedom equals to 17. The probability that this greater the value 2.9 is 0.005, and that's exactly what we are talking about here. So that means that value is 2.9 here. So the probability that this value, that the distribution greater than 2.9 is 0.005. So we are going to bring this 2.9 here. So we plug in 2.9 here. Now we are going to calculate the confidence interval. That will be like this. So it's going to be 12.35 and 13.45. I got a lot of questions during the class why this is 2.9. Again, we are trying to look for a value where the probability that this t-distribution greater than this value is 0.005, and this t-distribution has a degree of freedom, degrees of freedom equals 17. So given this being provided to us, it is going to be 2.9. So basically, that's what we have talked about during today's lecture. I know it's been short and it's not actually too much. Hopefully, we could make things faster in the future. Okay.